11.7 Volumes with cross-sections 2, triangles and semicircles. This is going to be very similar to our last lesson, 11.6, where we figured out how to find the volume if our cross-sections are squares and rectangles. This time we're doing triangles and then semicircles. So triangles. Well, we know that with squares, it's side length squared. With rectangle, it's side length times the height. While with triangles, the area of a triangle is 1/2 times base times height. So the volume of the triangular cross-sections is going to be 1/2. The base is going to be our side length, and times our height, dx. Okay. For equilateral triangles, the height of an equilateral triangle, for side length s, the height is going to be square root of 3 over 2 times s. So for equilateral triangles, the volume will be 1/2 times side length times square root of 3 over 2 times side length again, dx. In other words, the area is going to be 3 over 4 side length squared dx. And just starting not 3 over 4, but square root of 3 over 4. So it'll be the integral. So for equilateral triangles, it will be the integral of square root of 3 over 4 times side length squared dx. But for triangles in general, it's just our area of a triangle, 1/2 times side length times height, times our dx, integrated from a to b. Okay. For example, we go back to our same region as the last lesson. Let R be the region enclosed by f of x is equal to square root of x, and g of x is equal to x squared. R is the base of a solid with triangular cross-sections perpendicular to the x-axis. The height of the triangle is 3x. What do triangular cross-sections look like? So here's our region again. We want triangular cross-sections. If they were equilateral triangles, they would look like this. Here are our triangular cross-sections. And our entire volume would look like this. There's our entire volume. Okay? Cross-sections, the entire solid. So again, the volume has to be the area of a triangle, 1/2 times side length, which is the base, times the height, times dx. That's going to be 1/2. Our side length is f of x, is f of x minus g of x. Our height is 3x times dx. So that's going to be equal to square root of x minus x squared times x. And we can pull out the 3/2 out in front. So it's 3/2 times our integral from a to b of square root of x minus x squared times x dx. And really, the square root of 8, the integral is, we're really integrating now from 0 to 1. Once again, we can go to Wolfram alpha to calculate our integral. So we want to integrate our function is square root of x, square root of x minus x squared again times x from 0 to 1. When we do that, we get 3 over 20. So our answer to volume of the solid is going to be 3/2 times 3 over 20, which is equal to 9 over 40. That's the volume. Okay. Next, semicircles. So instead of triangles, like this, we have semicircles. Semi just means half of a circle. So our cross-sections will look like this, and the entire solid will look like this. With semicircles, well, the volume of a triangle is 1/2 times base times height. So we had 1/2 times side length times height. For semicircles, the area is 1/2 because it's half of a circle times the area of a circle, which is pi r squared. So let's include pi r squared. By the way, if you're trying to type a special character on Google Drive, on Google Docs or Google Slides, you can just go to Insert, Special Characters, draw your character here, and then click on it, and that's it. So it's 1/2 times pi r squared. That's the area. So the volume will just be 1/2 times pi. Okay. What is the radius? The radius is half the diameter, and the diameter is given by the side length. So it's really side length divided by 2 squared. Okay. Don't forget to divide by 2. We can see that here. Here's a circle. So side length is really diameter, but we need radius. So we have to divide by 2. Multiply by dx, of course. So that's what we can use to find the volume. So let's go to example 2. Same region. Let R be the region enclosed by f of x equals square root of x and g of x equals x squared. R is once again the base of a solid, but this time it has semicircular cross sections perpendicular to the x-axis with diameters extending from f of x to g of x. Find the volume of this solid. So the volume again is integral from a to b, the area of the semicircles times dx. Area of the semicircles are 1/2 pi times the radius, which is going to be our side length divided by 2. So f of x minus g of x divided by 2 times dx. And that's really just equal to 1/4. Our integral, so this time we know that we're integrating from 0 to 1 of square root of x. Oh, so after we divide by 2, of course we have to square it because it's the radius squared. So square root of x minus x squared squared. This is the diameter. The radius is half that, but we already took out the 1/2. We have to be careful here. This will be incorrect. Why? Well, it's divided by 2 squared. So we really have a factor of 1/4 in front. So it really should be 1/2 times 1/4, which is 1/8. So that's why I should be 1/8 out in front. Okay. Because we have 1/2 here, and then we have another 1/2 squared from our radius as half of the diameter term. So it's going to be 1/8 times pi times the integral from 0 to 1 of our side length, which is square root of x minus x squared, squared dx. Okay. So let's, this time we don't actually need to use Wolfram alpha anymore because, well, we know this is pi over 8 out in front. We've already seen this integral many times from the last lesson. The integral from 0 to 1 of square root of x minus x squared is just 9/70. So that's going to equal to 9 pi over 560, which is about 0.0505 if you do the calculation. Okay. So this volume is a lot smaller than the one with the triangular cross sections with height 3x. As we can see, this volume is much smaller than that one. Last time we got 0.225, and this time we get 0.0505, which makes sense. So what did we learn? If the cross sections are triangles, then the volume is just the integral of the area of a triangle dx, which is equal to the integral of 1/2 times side length times height dx. For equilateral triangles, the height is square root of 3 over 2 times our side length. If our cross sections are semicircles, the volume is going to be 1/2 pi r squared dx integrated, which is equal to the integral from a to b of 1/2 pi times our side length over 2 squared. Okay, that's it.